Hey guys, so this is another calculus word problem. And so this belongs to a category that people typically call related rates because they're usually functions of time and they're usually defined implicitly. Quantities that are functions of time that are related, and usually the way they're related has something to do with some mathematical fact. So typically what you do is you read the problem, and if you can, you draw a diagram and you label the parts of the diagram. You need to try to come up with a relationship between two quantities that are relevant, and then usually take the derivative with respect to time, which is usually using implicit differentiation there. That's why they usually this comes after that in most calc courses. So any self-respecting calc course is going to have a section on related rates, and sometimes the problems are contrived, but at least they're quote unquote real world. So you're kind of applying the some of these calculus concepts to something in the real world. So this is one that you see. There are like 9 or 10 of them that are, if you can master them, you can kind of get all of them as kind of templates. But here you have a light. So it's on top of a 20-foot pole. And there's a man walking to the right, directly to the right. And he's 5 feet tall. He's walking at a speed of 6 feet per second. And usually there's one or two things they can ask. And how fast is the tip of his shadow moving? That's one thing you can ask when he's a certain distance away from the pole. And how fast is his shadow growing? And they sound like they're the same, but they're not quite the same. They're related, but they're not quite the same. And so, to save time, what I did was he's moving at 6 feet per second. He's 5 feet tall. And so I labeled this same diagram. I labeled it. There's the pole there on the left. There's the man. And he's walking to the right, if you would imagine. And one of the things that is probably useful to know is that these are right angles right here. And so there's the light beam going down. And what I did was I labeled, there's 20 feet, side of that triangle is 20, side of that triangle is 5. And there's two quantities here that we care about. One is m and one is s. So m is the distance of the man from the pole to the man, and s is the distance from the man to the tip of his shadow. So you would imagine the light beaming down, and it's going to cast a shadow. And we're assuming all the lines here are straight. We're assuming that the pole is completely, it's not it's completely flush with the ground. It's a right angle. The guy is standing straight up. He's not drunk. He's not stumbling around. So there are these idealized suggestions, assumptions that you have to make in order to solve the problem. So he's moving at a rate of 6 feet per second to the right. So that's where we get this derivative. And that's where you almost have to know when you hear that, especially if you hear the word rate, that dm dt, that's what dm dt is. It's 6. And we'd like to relate that to S. So we would like to get ds dt. So we want, because that's going to take us very close to, that'll actually solve the second part of the problem. Because the length of his shadow is really from the man to the tip there. It's that small thing, and that really is ds dt. It's not quite the same as the distance of the shadow from the pole. But anyway, so how do we do this? Well, we need some kind of a connection between S and M. And if you look closely at this, you can see that there's two triangles here. There's this big triangle that's M plus S is one leg and 20 is the other. And there's a smaller triangle that S is one leg and 5 is the other. And they're similar because they share this angle. They both share this right angle. And they share these two angles have to be the same. Well, they have to, all three of them have to add to 180. That's one reason. And another reason is you have two parallel lines here if you were to extend that line. There's a theorem in geometry I think would give it to you. But so it's geometry that gives you this, and it's really the key geometry fact is it's similar triangles. This writing board is not the best. So similar triangles. And that's the other thing about related rates problem is to usually when you want to come up with this, relate one rate to another, you have to get an equation, some kind of equation, and there's some math fact in there or something even just common sense that would give you it, like the whole is the sum of its parts or something like that. So similar triangles means that corresponding sides, their ratios are the same. So that means if I take this big triangle, the one side, m plus s over 20, that's the ratio of the legs of the big triangle. That's got to be equal to the corresponding ratio of the legs of the small triangle, which is s over 5. And now you look at this and you can think if you have some experience with algebra, you should be able to either solve for m or solve for s. And well, if I quote unquote clear the fractions, meaning multiply the top and the bottom of both by 20, I'm going to get m plus s. Well, 20 divided by 5 is 4 is equal to 4s. And if I subtract s from both sides, I'm going to get m is equal to 3s. So that's my connection between m and s. And so let me go to the next one here. So this is what I got. M was equal to 3s. And so first of all, if dm dt, so I could take the derivative of both sides, and I would get dm dt is 3 times ds dt. We're really using implicit differentiation there. Like derivative of 3 times a function is 3, but then you got to multiply it by the derivative of the function. So if you solve this this is equal to 6, right? dm dt is equal to 6. So you're getting 3 ds dt is equal to 6. Solve that, divide both sides by 3, you're going to get ds dt is equal to 2. So that means his shadow is lengthening at a rate of 2 feet per second. That's really part 2 of our problem, right? Now, so that's his shadow lengthening, getting longer, lengthEning, shadow lengthening. Now, what about the tip of the shadow? So the tip of the shadow, so the distance from the tip of the shadow, that's that. What's the rate at which that distance is increasing? Well, the thing that's not moving here is the pole and the ground. The man is moving. So this ds dt is how it's moving relative to the man. But how much is it moving in an absolute sense? Well, that's 4s. So the tip of the shadow, the length of the tip of the shadow is 4s as a function. shadow, that's 4s. 3s there from the pole to the man, and then another s. 3 plus one more s is 4s. So we want the derivative of that. So the answer to the first part is d of 4s dt, which is 4 ds dt, which we already found ds dt to be 2, so it's 8 feet per second. And excuse my writing, but so yes, so the tip of his shadow is moving at the rate of 8 feet per second. So the man's going at 6 feet per second, and the shadow is ahead of him at this point at 2 feet per second. And this is going to change as he goes along. But so now let's make sure we've got that. So 8 feet per second is the shadow, and he's lengthening at 2 feet per second. So this one is 8, and this one is 2 feet per second. Feet per second. That's how fast the shadow is growing, 2 feet per second. And the tip of the shadow is 8 feet per second. And I just thought I'd do both at the same time because sometimes you see, and I think it gets a little bit subtle there when you're thinking about, because you really have two things moving and what you're really asking, and you see two versions of this problem because sometimes they'll ask you, how fast is the shadow lengthening? Well, they mean the shadow from the man to there. They mean that little distance. And if they ask you, it's all in how it's worded. How fast is the tip of his shadow moving? Well, that's absolute, the tip from the light pole. So it's all a matter of whose perspective, either the perspective of the light pole or the perspective of the man. So that's what gets a little bit subtle about this. And you notice how far he is from the pole is not even relevant. So that's another example. A lesson to be learned there is that sometimes people will throw in irrelevant information. So that he was 10 feet from the pole doesn't matter at all because we didn't use that. If you look back, you can replay this, you'll see we never used the fact that he's 10 feet from the pole. So this one was a little bit longer, and I hope I explained it well, and I did a little bit of a different take on it. But if I have time, I'm going to try to do these, and every couple of days. It takes a lot longer than I thought to produce these because you have to really get it organized to do a smooth presentation, and so we'll see. If you happen to stumble upon this video, I know this is a new channel, so this is going to be buried deep within YouTube. So if you do stumble upon it, please make a comment. If you could like the video, subscribe to the channel. It'll move it up in the inimitable YouTube so-called algorithm so that people can find these videos because there are plenty of high-quality videos on YouTube, but they get buried and kind of the big dogs end up dominating, and you can never see, if you were to do a search on this, there might be 100 videos that would show up before this one does. That doesn't mean those 100 are any better than this one, though. So, all right, thanks a lot, and hope you enjoyed it. Hope you like my little diagram.